Welcome. In this lecture, I want to go through what the equivalence classes of congruence mod 3 looks like, right? Because remember that congruence mod 3 is actually an equivalence relation. Okay, so recall first the definition of equivalence class. So recall, right, we have that, right, the equivalence class of X is going to be the set, is by definition, right? And here S is a set, right? So suppose S is a set. Then we have that the equivalence class of X is by definition going to equal the set of all S and S, such that, which order does this go in? That S is related to, but it's equivalent because it's an equivalence relation to X according to the equivalence relation. Okay, so in our example, we're going to let our S, so set S to be equal to the integer Z. I'm smiling because I remember to say Z. Okay, and our equivalence relation is going to be, so our equivalence relation is, this is actually, this often confuses students. We're going to write that so A is equivalent to B. And there's this if and only if in here. And sometimes when students are asked to do something with equivalence relations, they say, but this is an if and only if. When I'm proving this is an if and only a statement. No, this is actually the definition. Okay, I'm telling you when A is related to B. Okay, and it happens when we have that A is congruent to B mod 3 in this particular circumstance. So A is congruent to B mod 3. Okay. So then what are the equivalence classes? For this particular equivalence relation, we're still in that example. Okay. So the first one is going to be, so we need to have the equivalence class of 0, right? So this is the set of all, right? So this is minus 3, 0, 3, 6, and so on. Okay, that's one way to think of it. It's all the multiples of 3, i.e. it's equal to the set of all 3. So we have 3k, such that k is an integer. Uh-oh. I've used all my colors very excitedly. The set of all 3k, such that k is an integer. Oh, the integers are red. Okay, the set of all 3k such that k is an integer, right? i.e., right, everything that is congruent to 0 mod 3. So congruent to 0 mod 3. Okay. And then 1. So the equivalence class of 1, which is going to equal, oh, there's an additional notation for this one, actually. I think we've seen this notation before, where I write this. This can also be written as 3z. Okay. And then we have the equivalence class of 1, which is equal to, now we add 1 to each of these. How do I add 1 to minus 2? Minus 3, I get minus 2. Then I go 1, 4, wait, from 6 to 7. Then we just, actually, the trick is to keep adding 3, right? Okay, which is equal to, now we have the set of all 3k plus, look at this, so it's not a coincidence, plus 1, such that k is in the integers, right? So we sometimes denote this like 3 3z plus 1. Okay? i.e. everything congruent to 1 mod 3. So i.e. everything congruent to 1 mod 3. And then we have one more. So we've done 0 and 1. And then the last one we need, and that's actually going to be the last one, is going to be for 2. And so now we're going to say, so oh yeah, I could do -1, but let's do so -4. Yes, that is okay. Dot -4 -1, and then we add 1 to that, so 2, and then we keep on adding 3. Yeah, I'm doing great. Okay, great. So this is equal to the set of all. So now we have 3k, but it's going to be plus 2, like that 2 there, such that k is an integer, right? Which is, so we can also write this as 3 times the integers plus 1. It's kind of funny notation, or plus 2, sorry. But it's a way to do this, i.e. everything that's congruent to 2 mod 3. So i.e. everything congruent to 2 mod 3. Okay, great. So, actually, I'm going to show you this trick now, and then you'll see, and then I'll show it to you again later if you want. Okay, so here's like, if you notice this, this was actually, I don't know if somebody showed it to me this way or I kind of came up with it this way myself. Whatever the case was, this actually this allowed me to solve a lot of problems that maybe some of my peers weren't able to. I'm a very visual thinker, so if I don't have a way to visualize things, then it's all over. Okay, so we know that we have, if we're going through, we can put like, so 0 goes here, 1 goes here, 2 goes here, and then we start over and we go 3 goes here, 4 goes here, 5 goes here, and then we start over, and then we go 6 goes here, 7 goes here, 8 goes here. And then this is -1, -2, -3, -4, -5, -6, and then you'd keep on going like that. Okay, and that would actually give you those equivalence classes. Okay, and you'll notice that everything in here does differ by a multiple of 3. Everything in here does differ by a multiple of 3. Everything in here does differ by a multiple of 3, because that's what it means to be congruent mod 3, right? Okay, so I hope that made some sense and was a little helpful with the definition of an equivalence class, and I will see you in the next lecture.